semester. We'll do our housekeeping announcements and all next time when we have the student version of the seminar. So today, let me just get started with our proceedings. I'm very happy to kick off the semester with a old friend, colleague, energetic guy, Najim Dehak. So I know Najim from about 2007, 2008. He actually came to us for a summer in 2008. He was a student member of a summer workshop team. And in some sense, that started his claim to fame. I mean, his claim to fame is bigger, but that's the workshop at which he came up with this idea of I-vectors. And there's a little funny story. There was this idea that, oh, there's going to be a speaker subspace, a channel subspace, and all this other stuff which was not related to the speaker. And Najim discovered that all that other stuff has a lot of speaker information as well. So he decided, what the hell, this is a bad idea. Let me just start over and say everything is speaker dependent. And that's how this I-vectors came about. Anyway, so since then he's gone on. He started off in Algeria with a bachelor's degree in computer engineering, I think. Yeah. And then master's in Paris and PhD in Montreal. And now he's at Lincoln Labs where he's a research scientist. And he's going to tell us about I-vectors and actually what he's been doing since his original invention. And this might be something exciting coming up. So Najim, tell us.
Okay. Thank you so much, Sanjay, for the introduction and for a wonderful invitation. It's always a pleasure to be here since I feel like my career started here. It's been 2008. 2008, I was given a talk here as a student, freaking out. So I had, since that time, I did some move. So today I will be presenting my latest work about using the I-vectors in terms of new way to use the DNNs for the speaker or language recognition or whatever application you want in audio classification problem. But before that, I would like to go step by steps how I end up working in this new topic. And the way we're going to do it is, show you how we went from the I-vectors, which is actually related to some Gaussian Mixture Model for speech. And then after that, I'll show you some application, but only to do some data visualization to show you that what you can do with I-vectors, and then doing classification, you can do also visualization and see all the problems. Then after that, I will show you I moved the direction to do some work in the GMM weights because I-vectors was related to the GMM means adaptation. So I was doing some GMM weights, and after that say, oh, that's just a posteriors. DNN has posteriors, so let's just try and do some DNN stuff with it. And that's what I ended up doing in my latest work. And I show that, the way people are using DNN maybe is missing some information that people are not using. When they look the whole DNN, they only model one layer at a time. But you can also model the whole DNN together in one and make one decision. So that's my point of this talk. So as you know, probably the majority of you know, the I-vectors became very popular in the audio classification problem and also in speaker adaptation. Even now people are starting using it for adapting the audio to model for speech recognition from the speaker by using I-vectors as input for the DNNs. It seems to work very well. And the I-vectors actually was a new way to compact all the information of recording of different length in the same subspace. So we can compare audio, even they are different length, you can still compare them in the same subspace. So, and then after that, when you get this space, you can open a Bishop book in pattern recognition and do whatever you want to get to which information you want. And that was actually the beauty for it. Everything was actually about the I-vector was related to the Gaussian Mixture Model because you know how the species is a complex distribution. So we do a Gaussian Mixture Model to model this, to approximate this distribution, and we use I-vectors to model all the variability that all the phenomena, all the variability that was seen in some corpus. And I-vector will see, okay, this is my prior about all the sounds, how they look like in this space. So if you have a new sounds, I will just map it in this space, and you can do classification after. That's the good for it. So that's, I say, I moved from doing an I-vectors in the means to an I-vectors in the weights. There's a lot of variant from that, and I can show an overview about that, and I show how I went to my latest work and used that for DNN activations. So the goal from that is use this subspace to model the neuron activations, and you can also model one hidden at a time or whole DNNs to model the path of activation, which I call that. So so let's start, to show you what's the meaning of the I vectors if people are not familiar. Sorry if people know that. It may be a little bit bored in the beginning, but it would be hopefully it would get exciting by the end. So for audio, you have a stream of audio. Usually what we do, we transform this audio to extract some features. We call them structural features or PLP, whatever you want kind of features. Then after that, since the distribution and the composition of the speech is different phonemes, or different channels, this can affect your distribution, and this can become a complex distribution. So that's why we usually model that by a Gaussian mixture model on top of these features. So a Gaussian mixture model is just a summation of Gaussian weights, and you have a weights and how much proportion of the data. So each Gaussian has weights, mean, and variance, and So in speaker recognition, usually what we do, it started early in the 20s when Dr. Ronell started with his work is, so for example, I try to do speaker recognition for my speech. So I can take all your recordings for example, recording from all of you guys, a lot of data. So I can train a big GMM. And when you have a new recording from me, what usually we don't have too much data. The problem is, so we have like a week of data. So we usually adapt your Gaussian mixture model can play a role of a prior of how the sounds looks like. So when you have a recording from me, we only adapt the weights, for example, or the mean, from the GMMs to direction of my speech. So it means that the way that the universal background model, which is your model, the prior, the way he moved from a specific recording or a specific speaker can describe something. This movement can describe something. So it's something happened in this recording that this shift is happening. So that's exactly what so this is how people start using map adaptation from that. That's the first thing. And then there were also different approaches like MLLR, eigenvoice, and Joint factor analysis. Joint factor analysis try to separate between the speaker effect, channel effect. That's what Sanjeev said in the beginning. And the I vectors say, no, I would just want to see all the variability, what all the variability looks like in this older recordings, and then after when I get the new recording, I just try to map it in this space. So it's exactly this idea. So when people start looking to that, for example, you can see the two measure works that I can see is, for example, Patrick Kinney works in the earliest, around 2005 or something like that. He was trying to see, okay, the way that the universal background model shift to direction of the speaker of some recording can have an effect of it has two effects. It's based on two effects: the speaker, which is the information that you want for speaker recognition, and the channel, that's something you want to remove. Okay, and lately we find out that the way that it was built, there's some information in the channels, and that's why we combine them, and we had the I vectors. That's exactly what happened. And also we have the work of Bill Campbell when he say the way he modeled a supervector machine, tried to model the way that the GMM shift as a kernel, and use that for an SVM, and so each speaker has an area in the SVM that you would use it. So there's two things. So people start really looking to how the universal model move from one recording to another recording and try to model that. That's exactly the idea behind that. So the I vector, suppose you have a subspace, and you have the universal background model that like a prior. So this is like a 1 point in the space. So if you have a new recording, for example, it's a 1 point in this space. So what we are doing in the I vector, actually, we are just taking a lot of recordings, trying to learn all the variability of all these recordings and model that with a low dimensional space. So that's what we're doing. So we took a lot of recordings. All these recordings became, they can have a 1 GMM, for example, and then we try to see what's making this GMMs all different, and model that in a low dimensional space. So now when you have a new recording, it's actually easily, and the origin is the space is the universal background model, it's the prior. So originally, you have each recording actually is just each recording his GMM is actually the mean, which is the universal background model plus an offset, which is actually the I vector subspace, and the W is the one who was actually the I vectors, the one describe the movement, what happened in this recording. Something happened, that's why I have this movement and this shift. So it's exactly this I vector. So the idea behind that is when you train, we have an EM algorithm or PCA. There's a different way to train it. So when you have this subspace, when you have a new recording, you just try to map this new recording to this new subspace, and you will get your I vectors, and you are done. So now after that, you can do whatever you want. And usually, to be honest, I vectors, what we name for I's for intermediate representation, because usually we are working in the GMM supervector space, which is the concatenation of the means, which is a couple of hundred of thousands when you sometimes, to when MFCCs usually is about 60. So I vectors are about 400 to 600. So it's like an intermediate between the big size and the small size. So this is what we call it. That's what we name it, I vectors. So and then after that, you can do whatever you want, machine learning technique that you like. For which types do you want? No, no, they don't want to support that. Unfortunately, they didn't give any money for that. Unfortunately, so here, like, to be honest, I'm not going to give you anything about teaching you how to do speaker ID or language ID. I'm just trying to show you some cool visualization that we did. Because usually, when we do a speaker recognition, we give numbers. Say, oh, my equal rate went from 0.6 to 0.5 or something like that. So people get excited, but we really didn't see anything. What's happening in the data that you're improving something? So at that time, I was working with Lincoln and okay, let's go skip. I was working with Lincoln for 2010. It was actually Zahi and Karam, who was a PhD student with Bill at the time. So we start looking to what we can do in the visualization. So we had an I vector to work in telephone and channel the data, which is NIST 2010. So we took NIST 2010, and we have an I vector trained in the telephone and microphone data, and we selected about 5,000 recordings from telephone and microphone, and they would say, okay, what happened when we do channel compensation? What happened when we don't do channel compensation? How the data looks like? So what he did is we took the recordings and we compute the similarity, cosine similarity, okay, or distance, and then after that we build the three neighbors graph for each recording.
Before you go on, what you're saying is there's a universal background model, and for each of these 5,000 recordings, you do the map adaptation, you compute the shift of the means, compute the I vector.
Yeah.
And so now for each of the utterances, you have one I vector.
Yes.
And for any pair of I vectors, what is the distance between them?
The cosine.
The cosine of the I vector.
Yes.
Okay.
Cosine similarity between the 5,000 recordings.
Yeah. So it's a 5,000 by
5,000.
similarity matrix.
Yes.
Value is the cosine.
Yes. And then after that, we build from that this similarity matrix. We build the three neighborhoods. So each node
you get three.
Yeah, he be related to his three neighborhoods. So we have a graph, and we use GAS software to visualize this graph. And this is what happened. This is a female, so the colors is by females. This is clusters, so you see sometimes there's some connections to each neighborhood, and this is the cluster by female. This is the whole system. This is microphone, telephone data. We were the first one actually that for NIST that tried to not separate between telephone and microphone. We modeled them together, and you can see the separation. This is female. So what happened when I don't do channel compensation like LDA or PLDA? What happened is, we lose the speaker clustering. Something happened in the data. And some visualization, some clustering happened that at the time, we didn't know what's going on. And so we were talking, and after that we say, okay, well, let's go look at the keys. And after that, when we looked at the keys, actually it was the channels. So the channels you can see, and also the channels has also two clusters. We say, what happened? Actually, it was, this is when you focus on the telephone, this is when you focus on the microphone. NIST used 2 rooms in LDC. 2 rooms to train your channels. That were actually in the data. So we were like, wow, this is the first time we saw that. Like, it's like, I was not excited about how much they correct, or I was more excited to say, okay, well, we can see the effect without doing anything. Like, the data speaks by itself. And that's the for female. For male, actually, this is when we do channel compensation, but the coloring is still with channels. So we can see that the LDA is trying LDA or PLDA trying to clean the recordings actually to make the cluster more a speaker than the channels. So this is male. We try to recognize more male than female. Somehow even the ladies speak more than the guys. We can separate more the guys than the girls. So I don't know why. It's still a big question. So it's just so this is male. So when we remove channel compensation, we also lose the speaker clustering. So it's also that the channels. So the channels, for example, this is the telephone data, and this is the microphone data, and you can still see the different channels and the different separation between the rooms. So if you don't do anything about your channel compensation, your data may be really affected by the channels, And this is one example. And we were able to do that here because we were able to mix the telephone and microphone data and then the same subspace and same I vectors, and then we can do the separation. So this is for speaker ID, and this is also the speaker after doing channel compensation, and with the coloring is with the channels. Yes. So this is just to show you that actually LDA or PLDA, whatever, try to clean up the channels and make the data more speaker information than channel information. So this is one thing that. So we did the same thing for language ID. So I did. For language ID, you have language verification or language identification. People probably are familiar with that. So what I did is I have a lot of bunch of training data. I trained my I vectors on it. So now what I took 2009 recordings. Yes. So I took $200 iterants from each class, 200 iterants from each class, and for language from the eval 2009, and then so we have 24 classes. It was 24 classes. 23 classes. And then after that, I did cosine similarity, the same thing between the 4,000 recording, 4,600 recording, and I built three neighborhood graph, and I did the visualization. So this is how all the class looks like, and you can see that how the closeness of the language. The problem here, guys, it's the GES has a 3D visualization, so it'd be good if you have a 3D visualization. It's you can manipulate. Here's one cut. So. For example, you can see English and English Indian here, English Indian and close to Indian Urdu. All the Cantonese, Vietnamese, Korean are clustered together. Russian. There's also French and Creole. They're close together because they have French together. So you can see that how all this languages, the I vectors are like, you can do this analysis and visualization and see what's really happening in the data because you have a distance, it's a space, so it's small space, so it's not like it's a huge dimension, so you can do things with it. So that's exactly. So that's why I don't want to show you anything like numbers or something. I just want to show you what you can do in terms of analysis. What can be done? You can show that what's happening in the data. That's why I like to go to this visualization. So now, as I said, the I vectors was actually related to the means, adaptation of the means. So lately, I had to switch from my direction because I have a visit from students from Carl Leuven in Belgium, and he was interested in the weights and everything, and he was like, okay, well, let's do it. So we started working on it all together with his supervisor, and we start looking into how we can adapt the weights. But the problem with the weights, it's they have this condition that they should sum to 1 and they should be always positive. So that's this constraint that is different than in the I vectors, so that you need to deal with. So there's a lot of techniques that do that, like maximum likelihood estimation, non-negative matrix factorization with the constraint that they should sum to 1, and the constraint is of non-negativity is already there. The Subspace Multimodel, which is Caldi and PUT are doing that, Bruno, and even some people from COE are using it now. The non-negative factorization is what we proposed at that time, which is the same as an I vectors. As a sum, you have an universal background model, you have a shift, but the weight that you should have, they have the constraint that it should be positive or non-negative and non-negativity. So the two things that you need to make sure that you have. So supposedly you have an universal background model, GMM. So the way we do adaptation is, like, for example, you have a stream of frames, and you compute the posteriors, and you try to maximize the auxiliary function. That is based on the weights here. So if you want to do maximum likelihood, you only accumulate this posteriors and divide by the number of frames, and you have the maximum likelihood. If you want to do a more smart way, for example, you can use the non-negative matrix factorization. You say that the weights actually can be split in two subspace non-negative, would they maximize the auxiliary function or minimize the callback level divergence with the constraint that the weight should sum to 1 and also non-negative because you are decomposing non-negative matrix in two non-negative matrices. So, and this is the paper that, for example, you can use, have been used for the speech recognition. This is NMF. You can use the subspace multinomial model, which is actually in Caldi. You can go work on the log domain, log probability. So you have a subspace here that is a universal background model, and you have a shift, and this will, the denominator will allow you to make sure that this should sum to 1. And this is what so in the result I'll show you, I will, for example, I will give you two data sets, one in Arabic speech recognition, which actually use our technique, and the NIST data, which actually use this technique. And I found out, to be honest, for some DNN posteriors, this one is actually much better because of the nonlinearity that the other one does not give. So, for example, this one has the ability, for example, suppose you have three Gaussians, and each point corresponded in one recording, okay, with his weight adaptation. So this approach that this approach that was in Caldi implemented and everything with that and everything can allow you to really fit the data. The only problem with it, you need to regularize that because it can overfit. Okay, so we do regularize that, especially for my application for NIST, I had to regularize that, otherwise it will overfit in the training data and will generalize as well. So in our approach, we say, okay, let's keep it the same mentality as in the I-vector style. We have an universal background model, weights, and when you have a new recording, there's a shift that happens. And this shift can be modeled by the subspace I-vectors. But our problem with that, and is like the weights should sum to 1, and they should be non-negative. So we develop an EM-like style to do the training. We estimate error by projecting gradient, projecting descent, and we fix error, and we do L, and we alternate with that. And this is the paper that we developed that for the Gaussian mixture weights for language ID and dialect ID with people from Brno, and they were in the paper. So as I say, you want to maximize your objective function, which is the that I showed earlier, the same as the same one is the maximum likelihood, and with the constraint that this should sum to 1. So this is just a vector of 1 to make this sum to 1, this constraint, and this should be positive. And we use the projected gradient descent to implement that. So there's a matrix that makes sure that everything, when we do that, all columns of L should sum to 1, whatever R is, and to make sure that it happens. So the difference between, for example, the subspace that's, for example, in the Caldi that it was using versus ours, suppose you have this kind of data. So this one is really, the nonlinearity help you really to model how all the data looks fit. But this one give you an approximation what all the data is actually located. It's good sometimes to not overfit, but sometimes it's, when you have a complex distribution like a DNN, when you don't control really how the procedure goes, this one has to give you more flexibility, to be honest. So now, this is how we did the GMM weights. I'm not going to give you any result for there's a lot of references and papers that you can go refer to, but here I will tell you how I use this subspace technique for GMM weights to train to model the DNN's activations, which is actually this is my latest work. So suppose, yeah.
So when you're doing the GMM weight adaptation, was the idea that when you do the fitting of the universal background model to a particular session, whether it's speaker or language, in addition to the mean, you'll also adapt the weight? So was that the idea?
Yeah.
It's always done on top of the mean adaptation.
Yes. What we wanted is how much, because the problem is like what we did in the speaker ID verification community. Since the map started, we say, okay, we just need to adapt the means, but we never revised that because it's enough. But when we got the I-vectors and everything, we never said, okay, well, is the weights has some information, especially for language ID. For speaker ID, maybe it's not very important. For language ID, if you have a better, suppose you have a better clustering for your phonemes for your Gaussian as a phonemes, right, the weights can give you a good opportunity which phonemes are appearing, which phonemes are not appearing. Right. So that's why actually our motivation first. And that's why we start looking for it. What we start looking for is like, is there a way, for example, to adapt the weights, and then after that, create an I-vectors from the adapted weights?
Right.
So
when you do the Gaussian GMM weight adaptation, you're creating I-vectors only the weight adaptation.
That's only what, yes.
And so you can compare it with adapting the means, but you haven't put them both together.
I tried for speaker, it never worked out. I never tried for language. Which it makes sense. For speaker, I'm not sure, but for language, I was hoping that it will do something when you combine the two. But here, what I was shift, because when I was working in GMM weights, the DNN hit, so I had to switch a little bit and had to work on the DNN and then the I vector. So
take that idea, but now apply it to
DNN. Yes. So the idea here is like similar to earlier. You have a stream, you got features, and then rather than having a GMM, you have a DNN that will do something. For example, if you want to do language ID, you can. This is a paper that JHU, actually, he was here in 2013 in this workshop. What he did, he took the input, like some PLP features, for example, and the output was the language class. Okay, so you have a DNN doing the language ID, and after that, when you have a recording, he projects all the frames, then he averages the output, and he makes a decision which is the bigger one. So he got very gain in the short duration. He didn't work out for much for the. I will show that for the late duration, but I show now that we can actually get much better than by doing the whole DNN. So also you can have a C node, for example. You can have a DNN that model phonemes, or you can have a model speakers, whatever architecture you want. But what I'm saying here is the way that we are actually now doing DNNs for whatever task it is, we only use the output layer as a decision. Or we take some intermediate representation and use it as new features for our models. But we never actually looked to the whole thing. My point is, supposedly you have a way to say, okay, for each input, I only want 50% of my recording to be active. So you are forcing the DNN to take different path for this specific class. For example, if for a class 1, only these three neighbors, only these two neurons are active. But for these hidden layers, for the same class, he used these two neurons, and for this one is here. But so if you use only one DNN, actually you don't see how the activation went. But if you use the whole DNN, you will see that okay, for class A he chooses this way, for class B he chooses this way. You don't have that because you only make a decision in one particular hiddens. But you never say that how the hell he did it in different languages. For example, also if you alternate activation, for example, this one is sigmoid, and this one is linear, and this one is sigmoid. So maybe this information in this sigmoid after the linear or the rectified, the sigmoid has different information than this one. But we're not modeling them because our model don't see them at all. That's my point here. So is there a way? So that's why I'm doing that here. Is like, okay, well, maybe I should look to the whole DNN. The way I'm doing is like I'm modeling the information in each hidden layers, but I'm seeing also actually the whole DNNs. I can see the path. And that's exactly here what I'm trying to do. So the way we did it, for example, supposedly you have one input, you can compute the posterior distribution, sigmoid, and you get the probability of this. So, and then after that, for each frame, I normalize that. I normalize by hidden layer to make it sum to 1. So if I have a sequence of features, I can put propagate each frame, and I accumulate here. When I accumulate here, they became as a count, the same as the GMMs weight, by doing this trick of normalizing it. Okay, you can also impose softmax. You can impose softmax. And then for each frame, you propagate that and you accumulate. So you have accounts here. You have accounts here with the assumption that they should sum to 1. They should sum to 1, the same as GMM weights, and then and then after that you build a subspace. Or something we're working on it now is a little bit different. Say, I don't want to have any trick to normalize here. So what we do is, for each posteriors, we kind of double his and his complement. They became like his and his complement should sum to 1. It's just a trick to make it sum to 1. So the reason why we are doing that is actually was Lukács Berger criticism. Is like we want to give freedom to the range of the posterior distribution. How his range. If I normalize it, I lost the range that he goes. If I don't normalize it, I still model the whole complete DNN. I don't touch it. Because the other one are a little bit artificial. This one, the max and this one are more artificial because if I don't train with it, I'm imposing something that's not there when it's trained, you know. But for this one, I keep the same DNN. I'm just adding information that him and his complement. And when I accumulate, him and his complement became like a separate GMMs, small GMMs. And I have a subspace that can control that, with the constraint that each one should sum to 1. The subspace that SMM, NMF, everything can have this constraint. So now, by doing this, sorry. No, this is one runtime. So this is fixed. This is fixed. The one thing that people are telling me is, for example, if I want, there is a way to do it in a training. I can, for example, I can accumulate at some point, get the I vectors, get the errors, the classification from errors, and propagate that errors. You can do that. I'm not saying no. But here, I'm just trying to have a DNN doing some task, and you want to model the activation for this part. But there may be a way to say, okay, I can have a DNN, I can propagate, I can go to the subspace and say, okay, I'm supposed that should be the classification, and I can propagate the error from the subspace to it. There may be a way.
So here, no, I don't have any problem with
yeah.
trying to understand whether you add additional computation resources to runtime.
No. Yeah, we do. Here we do.
Or whether you can actually put that into a training paradigm that actually embeds the same algorithm idea.
Yeah, no, for here, I'm just in the runtime. The DNN is fixed. I'm not training DNN. Yeah.
No, but Najim, it's not runtime in the sense that it's not something you'll only do for the test data. What you do is you'll first train a DNN, you'll freeze it.
Yeah, no, it's freeze, I mean, yeah.
Rather than use the DNN as the classifier, for every input frame, you'll extract all the activations from the DNN, make this gigantic vector, and then build a classifier on top of that. For example, you're going to do your I vector.
Yes, but what I'm saying that in training time, he means train DNN. I'm saying I'm not doing that. The DNN is freezing. That's why it's runtime. It's like when we freeze the DNN and we do something with it.
So the DNN will become a feature extractor.
Yes. It means that he has some knowledge inside. I'm trying to extract it. That's it. It has some information inside that I want to extract it. Because people are using only the output or one hidden layers. But here I'm just saying that I'm trying to do, you can model the subspace here, and you can try to model them. That's exactly what I'm doing. So that's why when I say runtime, it's just more like, the DNN is freezing. Because a lot of people are saying, for example, if I want to do language ID, I can retrain a DNN based on the classification in the I vectors and try to propagate the errors. I don't know how to do it yet, but it may be possible. It's not like something I will say no. So now you can build a subspace in the first hidden layers, again, the subspace in the outside, and you can see how they perform. And I can show you the result that more you go deep, more better result. And if you combine, it's actually much better. So that's an example that I will show. So this is when you do like each one separately. And now you can use the I vectors trick, the non-negative factorialization, or this is just a reminder. You can use the I vectors to make sure that the weights should sum to 1 and should be positive. And So now what I'm saying, so usually we can do an I vectors each hidden layer, say. You can put an I vector in each hidden layer and you can stack them, for example. You can do that and see how much information you can gain. Or you can have one subspace that controls the whole thing with the constraint that each layer should sum to 1. Or each neurons, if it's neurons, the third trick should sum to 1. All this constraint that makes that probability still there to make sure that, that's one thing you can do. And then after that, you can do classification with it. And you can model the whole DNN. So in order to do that, you have a common subspace, and you have a ABM for each layer. This is L. And the weight for each layer, L is for layers. Yeah, each layer should sum to 1, but L and R are common for the whole thing. but the constraint that each one should be separate, and all of them, NMF, SM, Subspace Multinomial Model, the one in Caldi, and this one, non-negative factors, can allow you to do that. There's no problem. You know, it's easy extension. So now this is just an classification. So now here I will do it for dialect recognition task. We use some kind of simplify Van Misch's feature distribution or cosine similarity, something like that for language ID. So I don't think we can just skip this one. So here, this is the first task I did. It's Arabic data. We have a project with Qatar. So we have 5 dialects, train. This is how many recordings we have, train, dev, and eval. And we train a DNN that take the input. The input is filter bank at the time, and the output is the dialect. And this is the result. So I train a DNN of 5 layers. The first one is 1,000, the other one is 500. And this is the features, as I say, the features is speech frames, it's filter bank. The output is the dialect, is 5. And this is the best subspace dimension. It's actually, for this task, is full rank somehow. But, and the result are error rates, okay, of the classification. So this is the I-vectors, GMM shifted data capture. This is the I-vectors, it's around 20%. This is the Google trick. Google in so you take a DNN and you average the output and you take the max, and you can see that it actually was better because it's in our task the duration is very short, like 3 seconds or sometimes less. And that here, from here you can from this last 5 is I put a subspace for each hidden layers, and you can see that for dev and eval that more you go deep in the DNN, better the result here. And the error rate is going down. And also what I like about this, I always keep it, is that at layer 4, I'm already saturating. So layer 5, sometimes you put a lot of DNNs deep, but sometimes you don't need it. And here in this case, for example, between the 4 and 5, I didn't get anything. So I should stop at 4. So this is what I like about this result. It just shows you that sometimes you really want to make a deep just to satisfy yourself that you have a deep thing, but sometimes you really don't need it. And this result showed that after 4, I saturated. So, and then after that, this is just an experiment. What we did here is we compare a subspace versus just a maximum likelihood and divide the number of frame and do PCA and make a decision. And it's actually worse. So subspace was doing something in this case. That's why the way I did it. Okay, sorry. Yeah. Oh. Yeah. Oops. So this is the visualization, the LDA three dimension for the eval and the dev, based on the layer 5. So you can see that how the information is clustered. Well, but I used LDA. That's a little bit cheating. I didn't do PCA, but I used LDA. I should use the PCA for that. But here, so as I say, you see the I vectors. This is the DNN. This is all layer, even the output. And somehow, all hidden layers was actually giving me better. As soon as I added the output layer, something happened. It got messed up. So it was not good. That's why to be honest, I still didn't get it. So maybe I did something wrong there. But it means that this is the best layer. The last layer, which is 5 or 5 is same thing. And this is when you combine the all. So you still gain. That's what I'm saying. You can model each hidden layer. You can see that the more you go deep, better it is. Or you can model the whole DNN. And actually, it seems that to be much better for this case. We gain 2% more than it is. And I can show you that also for NIST evaluation, we had the same behavior. So I used our technique, non-negative factor analysis for this task. Here I'm using Subspace Multimodel, the Caldi one. And so I used NIST 2000 LRE. We did the same, tried to replicate the same what Inacio did. So we selected 6 languages that have the most training data. And you have telephone speech and Voice of America radio, but it's still telephone bit, narrowband, detected narrowband. So this is how many hours of training we have, and this is how many cuts in the evals from both cities and VOE for each one. So we say, okay, let's go with the one that has most data. So I train a DNN that takes the PLP features for this system, and the output is the language, 6 language.
How much speech in each test track? Is it
3 seconds, 30, and 10. There's, that is the result will be by that. Yeah, the result is by 3. So I took 5 layers of 1,000 DNN, and the output is 6. And this is this is a result by C average, the NIST metric. So this is the I vectors result, the best that we had with Lincoln. This is a collaboration with Lincoln. And this is the averaging the scores. This is the good trick, averaging the output and making the max. And they always claim that 3 seconds is much better than the I vectors, and it was true. So it's true. But for 10 seconds and 3 seconds, it was bad. And then after that, you see the hidden layers. And it's the same behavior. More you go deep, better the result is. And when you hit the 5 layers, actually, you can see that compare, for example, this with this, the output on this, you can see that this is a huge gain. If you compare with the I vectors, before what Google did was only good in 3 seconds, look here, it's actually better everywhere. So this seems that the hidden layers actually are more powerful and have more information, to be honest. And it's true because between this hidden layer and the output is just a logic regression. There's nothing really there. It's just a classification. So the more information is actually in the hidden layer before the output. So I'm saying that, the information is actually in the hidden layer that people can really go and extract it. And on top of that, I'm saying that if you model the whole DNN, it's actually much better. Here the result already is so low that I didn't get any gain. I was expecting a little bit that. But for 10 seconds and 3, we still get some gain, especially for 3, by combining the whole DNN. So it's still true that the whole DNN, there is still information there, and for both databases, it seems to work. So that's what I'm claiming. I'm claiming just, the way we're doing it, we're missing some information. We're not losing it, but it's there, but we're not using it. So it may be good to go and try to get it because you model the path of activation. Sorry.
So how big is this network?
This one was 5 layers of 1,000, 1,024.
So you have roughly 5,000 parameters or so?
No, it's times by times. Yeah.
more like 5 million?
Yeah. Yeah. So here, as I say, I'm using these tricks. I'm not claiming that's the best trick. I'm just claiming that, there is something there. I'm not saying that's the best thing you can ever find. I hope that someone find better thing. I'm just saying that it's maybe good to look to the whole DNN rather than just one layer at a time. Like, because I like Craig's comment earlier. That you say sometimes you learn that there's mistakes in each layers. If you take a decision in each layer, you don't see the mistake what happened before. But if you see the whole thing, you see the whole mistake before. I like this explanation. Thanks, Craig. Yeah.
So Najim, if I have to compare the Google method, the one that says DNN output versus your hidden layer 5, so the Google guys are accumulating the final output layer
and making a decision directly. Yeah.
And then they're making a decision by choosing the max.
Yeah.
And in your case, you're taking the layer before that, you're still accumulating, but then you're treating that as a high-dimensional vector, doing this
I vectors.
adaptation, extracting an I vector out of it.
And do Gaussian classifier.
And then do a Gaussian classifier on that.
Yeah.
So that's the difference between those two.
Yeah.
They have these layers which actually are not just flat, but or it's function of the vector. At each layer, they have kind of a hierarchy of sublayers.
Oh, they put the thing together like yeah. Microsoft did that too. Yeah, that too. To see it, but even I don't know how that compared do this one. I'm just saying this one was like analysis, but I know I'm more about it from the Microsoft sides. That you have like an input and you have a DNN, and after that you said you have the input, so you can still see what's it's called structured something. Yeah. I remember that one. Yeah, but this one I'm just saying that when you make it.
Is the coefficients of the network publicly available?
Which one? The
I mean, this
code?
no, this DNN.
Oh.
Trained DNN.
No, the DNN is Tiano. There's Tiano.
No, but I mean, you train it. So, I mean, training is a big deal, Do you provide the coefficients?
Which training? Training of the DNNs?
Yes.
Yeah. What?
No, Andreas is asking, would you give him your trained DNN?
Yes.
Oh.
Like Google gives the vision, they give you
Oh. Yeah, I will give. That's not a big deal. That's really not a big deal. It's Tiano code and the model is there, so we're free to. Yeah. I don't think there's a big deal with that. Yeah. No, there's the.
What Najim is saying is this is trained on a standard data set.
Yeah.
So in that sense, you can train it yourself.
I know, but it depends how long it takes to train.
Yeah. It may take a while.
The thing with the
Well, if-
project that Google releases is that model was trained on a lot of Google internal
And
data.
turn there. Yeah.
And we can never get that data.
No, talking about
That's why it's a valuable
the
model.
vision data set.
Yeah.
The big
Oh, the vision one I don't know about.
which is really, it's huge, it's massive.
Okay.
So it will take, so this is not as bad, I guess.
Yeah. Well, for whatever, for free guys to contact me, like, I'll be happy to share whatever I can. There's no the models, everything. Like there's nothing. I'm just saying that here that maybe we should really revise the way we're using them rather than just using them. And also like you can do a lot of things with that. For example, you can say, okay, I can have a lot of people with Hinex, he do that, do like 2 layers stacked bottleneck features. You can, but they should not maybe saying, okay, I can have a DNN, first DNN, extract the I vectors from it, and the I vectors actually go to another DNN to finalize the things, like 2 layers stack. But rather than just stacking 5 plus 5, that's the way that they do it, you can actually use this trick to model the whole DNN, get the I vectors, and go to another layer of DNN for phoneme recognition, for example. You can say, okay, I can go, for example, for frames, I can accumulate 1 second, make it get the I vectors, and the other DNN will follow that. So this is another way to do it. Yeah. Yeah.
So if you are using the whole network, is still, let's say, cross entropy the valid objective function?
Yeah. That's I'm still doing that. That's a good. Actually, this is a really good point because I'm facing now the problem is how much sharp I want to be. So the way we usually do it is we do the cross entropy, but the way we stop it by the error rate. Yeah, that's something, I'm finding that it's causing me some issues, to be honest. And this is a very good point. That I'm not really sure what's the best strategy to do it. Maybe I'm not the expert on DNN. Probably you guys have more, and Hinek have more experience than me, so he can point me that. But for that part, I'm not sure that I should really stick to cover the cross entropy and stuck with that, and don't do the other trick with. And I'm actually the DNN is running now. It's taken a while to train, but it's running now for that to confirm that point because I've seen some behavior. Because when you accumulate, you want that the map is so sharp. So when you accumulate, you don't hurt yourself. If you let it too much flat, if you accumulate, if there's some errors, yes, that's exactly the point I'm doing. So I want it to make too much sharp as much as I can because it will help me to really see what is going. Exactly that. So that's my point. That's a very good point that you're putting there. Yeah. So. Sure.
What you're saying over here is when people first started using DNN, they were simply using the output layer activation as some kind of classification score, like a probability or something, and they did classification with that. So if you go one step further and say, no, let's not worry about the output layer, let's take a bottleneck layer instead inside and think of that as a representation or as a feature extraction.
Yes.
So you're going one step further and saying, let's take all the hidden layers together and think of that whole thing as a feature extraction.
Yeah.
And then the question becomes, right? It's a
Yeah.
matter of
Yeah.
representation.
Yeah. It's well, in our I vectors for us is a feature extraction, so it's yeah, I know terminological. Yeah. There were like a lot of, when I gave this talk, a lot of people saying, well, you can, for example, for language ID, this task, as I say, your comment earlier, you can propagate the error from the subspace propagated back. It will slow down the whole process, but you will have a DNN actually doing what you want in your task.
Well, I like the idea of using more resources rather than really worrying about the serial aspects of training. If you haven't developed algorithms that allow you to the time,
Yeah.
don't exploit the argument.
Yeah. No, this can any architecture that have posteriors can be useful for this. It's not stick to feed forward. It's we're doing new things for speaker ID. For example, for speaker verification, what we're trying to do is having two DNN that tell you speaker different two segments are the same or not. So it's learning speaker variability. So it's different architecture than this. So we are doing that for now. This is going to be tied to any other architecture. I'm just saying that this way to model the neuron activation is one good way. It's not the best way, but it's one way. Maybe it's not the best to complete the best way, but that's one way to do it. I'm just saying that claiming that there may be more information that you think that the DNN contain that people are not using. That's the only thing. Well, I'm just trying to go inside the DNN and try to see how he's modeling. Here, this subspace models are really trying to model the DNN reaction. Exactly. Because if I give him one recording, he's reacting something. This is a point in the subspace. If he reacts another point, it's another point. So it's just modeling how he's reacting to a new phenomena. Like not a phenomenon, something happened in the recording that he's pointing at by looking at the correlation. That's true. Yeah.
And one more question, just going back to what Jen was saying. When people first started using these DNNs for modeling, there was this whole recipe which said, first you should do some pre-training using unlabeled data, and then you do this discriminative training or whatever, fine-tuning using the labeled data. But lately we've gone away from it. We just start with random initialization, simply do backpropagation training, because with a lot of data we get good results. But maybe you want to go back to the old recipe, because if you're simply extracting features... So, exactly,
Alan asked the same question just before the talk. Okay. My original work with that was, I want to do an autoencoder. Right. I don't want to force him to do any discrimination. I just want to code the speech. Right. Then after that, extract this speech in the I vectors, and then after that, do classification with it. Because when we are doing I vectors, there were GFA, there were speaker space, channel space. I vectors came unsupervisedly say, I want to model the whole thing. The same thing. I want to keep the same unsupervised concept. So I want to have an autoencoder. It can be generative training autoencoder, or it can be also autoencoder with discriminative training propagation. So two things, but exactly that. That's exactly what I wanted to do. Because for example, if you have one autoencoder in speech, I'm just modeling the speech. You can have an I vector say, okay, let me see if you have a speaker information. I can try it. Let me see if it has language information. I can try it. I can see how he modeled the phonemes. Because that's exactly what I'm going. I want to code the speech and try to see what's this DNN coded information it has. Yeah. But it's exactly true. So I want to come back to the revised. The autoencoder can be generative pre-training, layer by layer, or an autoencoder discriminatively trained by. Yeah.
Is there any reason why you're using Piano and not?
No, it's just because my student was there and he liked Python, and I was like, okay, I need Piano, and he just got me that thing. Well, there's no preference, to be honest. We were actually, the first experiment I did, we did it with our own code. That actually we were working with Lincoln for it, but it gets so, C++, it gets so messy and say, okay, forget it. Every time you want to change something, it's so complicated, so we just forget it. And to be honest, I compared between, like, I have a lot of students, everyone using Cafe was using CNTK. Tiano is giving me the best accuracy for now, so that's why I stick with it. Yeah. For me, it was more like that. Like, and I use Python, and so I'm more comfortable with it. So it's like keep it. Yeah. So perhaps we should conclude. So as I say, the whole history is went from an I-vectors from means to an I-vectors from weight, and then end up working in this DNN activations using the subspace. So this is like, as I said, there's different way to accumulate the statistics. This is, we just average the thing or sum over time. So one thing that I really want to explore is the alternating the activations. For example, you have a DNN that do, like, for example, sigmoid, rectified, sigmoid, rectified, sigmoid, rectified. So you enforce that the DNN change stuff in the middle, so that these consecutive sigmoids are completely different because they have a rectified in the middle that may have some useful information at the end. You're not satisfied, Andreas? I like the Autoencoder. And RNN architecture can be also useful, and try to use it for speaker ID to try to model the separability between speakers. That's one something. Explore the dropout. Then when you force the sparsity, that's something we're really trying to do. Imposing dropout, like how much you impose sparsity. So the way that the DNN choose the path is completely different between layers. So that may be useful. That's something really useful. Yeah. All right. Thank you.
Any questions from this side of the room?
This side of the room, meet me before the talk.
If there are no more questions, let's call it a day. Thank you again, Najim.
Thank you.